So the first thing is digital, and why do we go to digital, and why do we then compress? Well, I think all of us pretty much know now that the problem is that if you take a power signal and put it into an analog to digital converter, you end up with 270 megabits per second, which is an awful lot of data that actually, unless you've got a piece of fibre, you can't do too much with. And the whole world is now moving towards high definition, and that problem just becomes bigger. For 720 and 1080, 1.3 gigabits is what happens if you put an HD picture into an analog to digital converter. And so the world quickly realized that actually we need to compress it. So SDI, which is the 270 megabit standard, is still too long, is too big. And so we compress it. And as I say, high definition is even worse. 1080p 50, which is 1080p 60, which is what everybody's talking about now for the studio standards, is requiring a 3 gigabit studio infrastructure. And so we're never going to be able to transmit that amount of data over air or even in a commercial environment on the satellite. And so it is compressed. And in the broadcast world, as you know, we use two techniques, MPEG-2 and MPEG-4. And I think an important point here is that the broadcast industry is very much standards-based. Peter mentioned the need for standards in digital amateur television, and I think, you know, the thing about the broadcast industry is that it really has leapt on standards to ensure interoperability, and that's exactly the reason why we need, in the amateur world, to agree what standards everybody's going to be using, because unless we do that, we're just not going to be able to get the interoperability between the groups. And so we, in the broadcast industry, they really adopted MPEG-2 15 years ago, but what we're seeing is new standards coming along, MPEG-4, that I'll talk about in a few minutes, and talk about why we need it. Typically, we're seeing MPEG-2 compressing it down to rates 2 to 6 megabits for standard definition, and we're seeing high definition happening on some of the services now, with high definition being using MPEG-4, compressing it down to somewhere in the 6 to 8 megabit range. So the need for compression is absolutely there. We need to go to digital. We need compression if you go to digital. But both of the standards do use quite similar techniques, and I thought it was worthwhile just a couple of slides saying what are those basic techniques. And what digital compression is all about is basically fooling the eye and using algorithms to take out any of the redundancy within a picture. So there's two basic types of compression. One is what we call interframe, where if you look at this picture of Yosemite National Park, you'll see that in the area I've marked here called a macro block, the encoder would code that with luminance and chrominance information. But the thing is, if you note in this particular picture, that the next four blocks are very similar. So within a frame, we've got a lot of redundancy. And so what the implementations, what the compression implementations do is basically code one macro block and then say, refer to that macro block in this one and just say what the difference is. And so you can get an awful lot of efficiency rather than coding each one of these macro blocks. You code it one and just say, and the difference between this one and that one is this. So within a frame, there's an awful lot of redundancy. So that's one way that we achieve significant data reductions in the amount of data we have to send. And then the other one is between frames. And so what we call interframe compression is if we've got a picture, probably Yosemite again, we code that first picture, we would tend to code that with some great detail. But then we can then take the next frame, don't forget this is now a different frame, we can say what the difference is between this frame and the previous frame were. So it's basically in that area where the cloud has appeared is the only area where there's any information which is new to this frame. And similarly, we can go on for a number of frames, and there's an awful lot of redundancy between the frames. So we can now say, we don't code each one of these frames. What we do is we reference backwards and forwards to the previous frames to build this frame. And so we end up with a situation here where you'll hear those who know about digital, they'll be talking about groups of pictures. Now, generally, we take 10, 12 frames at a time. The first frame is called an iframe, and we code an awful lot of information. We put a lot of data into that first frame. We then code these frames at the back here called P frames, and we reference them to the iframe. But that's not all, because what we then do, from the information in that frame and that frame, we can then build this frame. And so by just transmitting the I's and the P's, we can then build up the picture of what's happened in the previous frames in between. So as a group of pictures, you're very much being very efficient in the way you code information, the majority of information going into that one. But of course, this explains one of the great mysteries of digital, in so much as you have to wait from the iframe through to the P frames to be able to build that complete picture, which is why you do get delay on digital transmissions. Basically, the encoders are waiting to get the collection of frames to be able to then interpolate between the different frames and calculate backwards and forwards what the differences are. So with digital, you'll always get delay. There are a number of delays that you take into account. Those of you who've got an analog television, a Freeview television and a Sky television will know that there's different delays between each one of them, because as well as having the coding delay, which can be probably half a second, you've then got the satellite delay, which is another 0.6 of a second on the satellite transmission. So digital is always going to have delay, but it is much more efficient than analog. So they're the two basic techniques that we use to generate digital pictures. But that's not quite everything that happens within the studio. Obviously, on all of the services these days, you have a collection of channels, and within one RF frequency, within one transport stream, we get a number of services. And so you have a number of encoders. The digital stream that you receive at home is much more complex than that. There's a lot of data associated with it describing that stream called the service information data. There's the conditional access data on services like Sky, and there's a whole management goes around it. And so the services really come together in a thing called a multiplexer, where we also do clever things, such as statistically multiplex together these different streams, and then the modulator. So if we move through the system and have a look, within the multiplexer, we're bringing together all of those services. So it's multiple videos and audios, the electronic program data, and we can bring standard definition and high definition services together at this point. And so within a satellite or a Sky multiplex, you probably see 10 plus channels. Within Freeview, currently it's around about 6 channels because of the differences in RF bandwidth. So putting it together as a multiplex, which then produces a bit stream, which is around about 30 to 50 megabits, depending upon the service you're looking at. That then goes into the modulator. Just as a point of reference for us as amateurs, basically this stage of multiplexing doesn't happen because we're only putting one service together. So the encoders that we use are a single service encoder called SPTS, single program transport stream. They generate a bit stream which just contains that one service. So we've now got that data stream, which can be anything between 20 to 50 megabits, and we then modulate it onto the channel that is in use. And for the different platforms, we get different types of modulation. So over our terrestrial network, the Freeview network, we use OFDM. Over satellite, it's DVB-S or DVB-S2, as we'll hear in a moment. And this is really the standard that we're now starting to use as amateurs. Over cable, there's another standard called DVB-C, which uses QAM modulation. And over IPTV, or over DSL, there's no real standard adopted. It's basically IP packetized. So the difference between satellite and terrestrial really is the difference in modulation. So the difference between Freeview and Sky is that Sky will use what's known as QPSK, and for us the significant thing as amateurs is that with modulation schemes such as QPSK, the bandwidth will vary with the bit rate. And this is why there's a little bit of debate as to what symbol rate or what bandwidth number of bits we should use for amateurs, and why on 70 centimeters we're saying we will run 2 megabits, because the bandwidth will reduce as we use less bit rate. And so the bit rate that we've chosen on, or we're looking to choose on 70 centimeters, is something around 2 megabits, which gives us a bandwidth of approximately 2 megahertz. The standard that Freeview use for the terrestrial television services here in the UK is called OFDM. Now, this was designed as a PAL replacement, and as we all know, hopefully, PAL, certainly in the UK, is an 8 megahertz standard, and so OFDM is fixed as an 8 megahertz bandwidth. No matter what bit rate you put it into it, it always runs at 8 megahertz. And that's one of the reasons really why it's not that suitable for amateurs, because first of all, we like the narrower bandwidths, because using the power bandwidth ratio, we can generate more power in a narrow bandwidth. And generally on some of the bands, we just don't have 8 megahertz bandwidth available for, say, 77s. And plus the fact we don't really need that amount of bit rate. So it's inefficient for us to run OFDM. Plus, getting linear amplifiers for 2 megahertz is bad enough, but getting them for 8 megahertz, and they need to be ultra linear for OFDM, is quite difficult. Now, one of the reasons why OFDM gets a little bit confusing in a moment, I'll have to explain a little bit more about OFDM when we talk about Freeview, is that QPSK is a single carrier mode where we modulate that single carrier on the satellite with quadrature phase shift keying. OFDM is multi-carrier, so within that 8 megahertz we have got 2,000 carriers, and each one of those carriers is then modulated using either QPSK or 16QAM. That is not to say they're the same as single carrier QPSK, but the carriers within OFDM are modulated using those same modulation types, and so it can get slightly confusing. When you dig into OFDM, you suddenly discover that it runs QPSK, but it's not the same. Well, it is the same, but it's not the same standard as running single carrier QPSK. So this was a drawing that an engineer at the place where I work came up with to try and explain the differences. QPSK, single carrier, very high bit rates on that single carrier. OFDM is multiple carriers carrying much lower data rates on each one of the carriers. And the reason why that's significant is OFDM was designed for use in the terrestrial environment where people expect it to work when they put the TV on the fridge and run the rabbit's ears. And if anybody's watched that, you'll see the ghosting and the interference that you get. And so it was generally, the perceived wisdom was that for that environment, something like QPSK was not robust enough. And if you get bad enough selective fading or frequency fading on QPSK, you will take out the main carrier, you will lose the signal. The key to OFDM is that you can take out a number of these individual carriers and still reconstruct the overall signal from the remainder of the data. And so to illustrate that, this is actually some 2.3 gig OFDM. So here, this is your 8 megahertz bandwidth across there. So within that space, you've got 2,000 of these carriers, each one of which are individually modulated, but only at a low rate. And what you can see here is some frequency selective fading, such that that null there is a good 20 to 25 dB down. It's nulled out a whole chunk of the OFDM frequency. If this was a power signal, that would be a massive ghost, an absolutely massive ghost. But the thing about this was that it didn't affect the OFDM signal. The OFDM signal was still received even with that 20 dB null actually in the middle of the signal, because it reconstructed it from the data, the redundancy of the data that was in here. And that's why OFDM was selected for the terrestrial services. On the other hand, this is a picture of some pretty appalling QPSK. I don't know why I continue to use this, but this was some of my early QPSK experiments. And this is a single carrier here. What these are, as Ian and one or two others in the audience will tell you, is what's known as spectral regrowth, which shows that even over 2 megahertz, the linearity of this amplifier really wasn't suitable for QPSK or digital operation. But you imagine if we tried to use that amplifier over OFDM in the 8 megahertz bandwidth. So, if you like, that was just a very quick skate across digital and digital technologies. But I felt it'd be worthwhile just taking a look at what's happening in the commercial world. And interestingly, MPEG-2, DVB-S, DVB-T have been around for about 15 years. But over the last 5 years, we're starting to see new technologies coming in. And that's because in the commercial world, there's really always this drive for efficient use of spectrum. I think, ATVers need to take note of this. Primarily, it's driven by the regulatory bodies in various countries, or it's driven by financial incentives. The satellite operators want to get more and more shopping channels in a given bandwidth because that's the way they generate money. And the governments around the world all are very, very interested in spectrum resale. And so if they can push the majority of the TV services to go digital, there is certainly a spectrum clawback, which then be sold on to the other providers who will pay money for the spectrum that the public service broadcasters currently use. So there's a drive towards more and more efficient technologies, and really what we've seen over the last 5 years is the introduction of MPEG-4 as a compression technology, and in modulation terms, DVB-S2 and DVB-T2. So what are they about? Okay, I think I've basically said this. One interesting fact, that MPEG-2, there's probably about 1 billion set-top boxes around in the world. That's the estimation that one of the commercial reports came out with at the end of last year. MPEG-2 is going to be here for another 10 years, there's no question about it, but MPEG-4 will come in and be used in certain areas. The main driver for the introduction of MPEG-4 technology was IPTV over your telephone line, over DSL. They need to get standard definition pictures at 1.5 megabits into the home. So, the first thing I'm going to say about this slide is there is a lovely phrase up here called bit rate required for broadcast quality television. And we could spend the rest of the day arguing over what broadcast quality television is, but this is really what we've seen happen over the life of MPEG-2. When it first started, when I first joined the industry, we were probably offered about 8 megabits for a premium quality channel on Sky, something like Sky. Those of you who've seen some early pictures, this was the days of what we call the 12U encoders, which were this high 12U, 12 rack units high. And over time, the implementation of MPEG-2 has driven the bit rate required for a given picture quality down, such that we're down at around the 2 megabit level. Probably the shopping channels on Sky are running around about 2 megabits these days. Sky Sports, Sky News will be up at 4 or 5 megabits, but a lot of the programming is in this area, 4 to 2 megabits. But that's still not good enough, and if we can drive it down further, you will get further benefits. And to give you an example of what's happening, the channel 4 MUX on Freeview was using a generation of encoders that gave around 3 to 4 megabit performance. Arkiva, who run that multiplex, have recently changed that out to some latest generation encoders, and they've got 2 extra channels in that Freeview multiplex, which Discovery, I think it was, paid over $10 million pounds a year for. So that's why we've got this graph running down all the time, why there's such pressure on efficient coding and efficient modulation. But it still wasn't good enough. The improvements on MPEG-2 weren't good enough to meet where the industry was going, and so MPEG-4 is coming, and MPEG-4 is going to be used in 2 places. First of all, the majority of the high definition services in the world, apart from America, where there is still some MPEG-2 encoding, is going to be using MPEG-4. So all of the Sky services, all of the Freeview services are in MPEG-4 ABC Part 10, to give it its correct terminology. Standard definition services, we're going to see MPEG-4 being used in what we call greenfield. And what we mean by that is Norway didn't have a digital television service for terrestrial until a year ago. And so rather than go to MPEG-2 and then upgrade to MPEG-4, because there were no MPEG-2 set-top boxes in use in Norway for terrestrial, they could start the service at MPEG-4 and get the efficiency gains, because there was nobody with an MPEG-2 set-top box to upset. The other place we're seeing it is in IPTV, or this television over your phone lines, because there again, nobody's got any set-top boxes. So it's going straight to MPEG-4. How good is it? These are some lab tests that we did looking at what's known as picture signal to noise ratio. And we took some material, and to achieve a picture signal to noise ratio of about 7 dB, you would require approximately 2 megabits using MPEG-2, using current implementations. To do that in MPEG-4, to achieve the same picture to signal to noise ratio, you're down at 1.2 megabits. So there is a significant gain to be had by going to MPEG-4, which is why the industry is going there. And similarly, on HD, you're getting the same sorts of benefits as well. MPEG-2 HD is up at the sort of the 12 megabit level. MPEG-4 over time has come down somewhere between 6 and 8 megabits. Now I appreciate this is all subjective. What is broadcast quality television depends on the content, but that gives you an idea of what's the snapshot of what's happening in the commercial world. As well as doing advances in compression, there's also advances in modulation. The DVB, which is the organisation based in Geneva, which comes out with all of the digital television standards, were very innovative in the name they gave the next standard. They called it DVB-S2. Makes sense. And actually, DVB-S2 uses some technologies primarily around the FEC coding, which were actually invented back in 1960 by a guy called Gallagher, a scientist called Gallagher. But up until now, really, the consumer devices just hadn't had the power to implement the standards. And so really, it's only in the last 5 years that silicon has been capable. As we all know, it's how many times? 4 or 5 times a year or something, the computing power goes up in a chip. So what we're now seeing is that DVB-S2, the consumer boxes are now have got the power at a reasonable cost to decode it. And so DVB-S2 has been introduced. And what it does for us is give some significant gains. And it's reckoned that actually the performance of DVB-S2 is only somewhere about a dB above the Shannon limit. And so somebody has been bold enough to make the statement that there's no redesign required in our lifetime. I don't know about that. Not only does it add additional FEC technologies, but also some additional modulation constellations. And the types of constellations we're now starting to see on DVB-S2, we've gone from QPSK over on the far side there through to DVB-S2 on the right conditions will allow you to do 32 APSK. And the benefits of doing that are that for a DVB-S system using QPSK, you're looking at the benefits of anywhere between 20 to 30% extra bits you can carry in the same bandwidth. So that's pretty significant when you're running 30 to 40 megabits already in a DVB-S system, to be able to get another 20% amount of data in that same bandwidth. That's the reason why we've gone to DVB-S2. And when you put that together with the gains that we've talked about in MPEG-4, put those together with the MPEG-4 and DVB-S2 gains, you know, the total bit rate and the total channels that people like Sky and Freeview can now carry, if we were to go DVB-S, QPSK, 27 megabits, high definition service in MPEG-2, you could probably run about 3 channels. Now, putting this package together, you're up at 7 channels in the same satellite bandwidth, the same satellite cost. But there's some other tricks around which people like ourselves are doing. Some of the technologies my company has been looking at is pre-correction of the constellation over satellite. So we've got some technologies which will take this typical 16 QAM symbol rate constellation off the satellite, and using digital pre-correction, we can, by correcting for phase, magnitude and group delay across the satellite, we can end up with constellations like that, which in terms of carrier to noise ratio can give you yet another significant improvement over and above the improvements we've seen. So that this is actually a commercial slide from one of our company presentations. So we've gone from the 2 or 3 HD channels in MPEG-2 right up to something like 8 channels using MPEG-4, DVB-S2 and satellite pre-correction. Just gives you an idea of the types of gains we're seeing from where we were 10 years ago. Mustn't forget DVB-T2. T2 does exactly the same for terrestrial as S2 has done for satellite, and so the types of gains we're getting in the current UK Freeview modes, 24 megabits when they run 64 QAM, using T2, 35 megabits. What does that mean? Well, it means an extra 10 or 12 megabits. That's an extra 3 or 4 services, and that's what it boils down to. So that's a look at the technologies. A few quick slides on the UK market. For those who weren't aware, there's 22 million TV households here and 5 major platforms: satellite, terrestrial, cable, and have to include BT Vision for completeness. Sky, I think that number is probably a bit low. This slide was written about 6 months ago. I think they're pushing towards the 10 million subscribers now. 300 plus channels because they've got unlimited bandwidth on satellite. And it's a mixture of pay-per-view, free-to-air and national TV services. Most of the channels are standard definition running MPEG-2. Reason for that is because they've got an awful lot of boxes that have been out there for 10 years, which are MPEG-2 standard definition boxes. However, their new high definition services are MPEG-4 and DVB-S2. FreeSat, and for those of you in the UK, this is the big secret. Basically, FreeSat is a complementary service with Freeview to enable 99.5% coverage by the time of analog switch off, which is the requirement under the legislation before they can turn the analog transmitters off. It uses the same transmission as Sky. FreeSat is an EPG. It's a guide, it's a program's listing. You go and buy a FreeSat box from Curry's, it uses exactly the same transmissions as Sky at 28 degrees east. You've just got a different electronic program guide which only enables you to see the free channels. So exactly the same satellite transmissions, just a different EPG. It's actually a good way to go. You can get more HD services on here at the moment than you can on Freeview. And particularly if you live in the south of England, that's going to be the case for the next 2 years. And FreeSat, really, I think they've got about 500,000 subscribers now. Virgin Media is our cable offering, about 3 million subscribers. Still run a lot of MPEG-2, standard definition and high definition, because in theory they've got plenty of bandwidth. Although they're starting to run out of bandwidth because they're offering such high data rates on the broadband service. BT Vision really isn't a true IPTV service. For those of you who don't know, BT Vision is a set-top box that you buy from a retail store. You plug your aerial in to give you Freeview TV. You plug your phone line in so they can download video on demand and movies to your set-top box. So it's a service that joins up movies delivered over the phone line and terrestrial television coming in over the area. Quickly, I just wanted to talk a little bit more about Freeview. This is the main service after analog switch off. It's currently, it has got 6 RF channels or 6 multiplexers from each TV transmitter. Currently, a lot of those services are MPEG-2 standard definition, running DVB-T, and it runs, certainly, as I live in the south of England, I can say this, it is currently standard definition only. But you may be aware that there's a massive re-engineering going on at the moment to the Freeview network. What actually happened with the original implementation of Freeview, if you rewind back to the 60s, the UHF spectrum in the UK was planned out for 4 services: BBC One, BBC Two, ITV1, and what was known as Channel 4. And that was the spectrum plan. Along in the 80s came Channel 5, so they re-engineered some of the spectrum. Channel 5 was transmitted either from the main site but at reduced power levels, or such as in Southampton, they couldn't put it on the main UHF station. It had to go on a subsidiary transmitter mast because of interference into the continent. So Channel 5 was basically squeezed in. What we've had in the last 7 or 8 years is that as digital comes along, Freeview was then interwoven in the channels between the PAL services. But to avoid co-channel interference, they had to run it at very much reduced power. And up until about a year ago, certainly all of the Freeview services generally ran at about 10 to 13 dB less power than the analog services, which is why Freeview coverage wasn't necessarily as good as your analog services. What's happening at the moment is there's a massive re-engineering program going on. They're rebuilding certain masts. Those of you who live up in the Lake District, I think Colbeck has had a new mast put up. In Norfolk, Tackleston has got a new mast put up. Massive re-engineering, such that by 2012 at analog switch off, they will be able to run full power on the Freeview multiplexers. As part of that as well, when they originally started the 6 multiplexers, they were running MKEG2, and there was they attributed the channels to various services, such that we had 6 multiplexers running a mixture of OFDM, QPSK, and OFDM QAM. So we were in the order of about 18 to 20 megabits, depending which. These 2 multiplexers here were generally the ITV multiplexers, which ran higher data rates, but the coverage wasn't quite so good. The plan post-switch off is to get every single one of those multiplexers to run 64 QAM as a minimum, and maybe DVB-T. And analog switch off, by the way, is 2012 for those of you who weren't aware. And so what's happening is by this year, they've actually started to run higher modulation on some of the other multiplexers. They've moved channels around, and the BBC has given back some spectrum. And that's all why we have, over the last year or so, had to retune our Freeview boxes, such that what they've ended up with right now is they've managed to free up one complete multiplex, which is this one in grey here. And that multiplex is a multiplex here that they're now starting to run high definition on. And so this is running DVB-T2. All of the other modern multiplexers are running DVB-T, but this multiplex here is running DVB-T2 and MPEG-4. And so this is the configuration they will end up by analog switch off, is that we will have 5 multiplexers running standard definition, this multiplex running high definition DVB-S2. There is a rumour around that by 2017 they'll all run DVB-T2. The disadvantage, of course, is that every single set-top box that's being sold at the moment can't really receive T2. It's only the set-top boxes that will be available from now on in will be able to receive T2. So your current Freeview box can only receive these channels. And for to get high definition on Freeview, you will need a DVB-T2 box. Okay, and that pretty much goes around. Summarised by saying it's a digital world. Every picture you watch, even if you're still using analog television, I can guarantee you has been digitised at some point in its chain. Unfortunately, the pictures probably aren't any better. There's a recognition of that. Digital will happen, and I think it will be the saviour of things like 77 ATV. So hopefully that's sort of given an overview of what's happening in the digital world and how things are progressing, given some of the reasons why we're having to retune and why some of the difficulties of receiving HD on certain things. So thank you very much.